Hello, and welcome to Physics 12, Dynamics, Lesson number 3, Advanced Friction. Here we will look at more advanced situations that combine the last two lessons together to create more difficult problems. Let's start with something we have seen before. What force do you need to move a 33 kilogram box if the coefficient of static friction is 0.56? Like all questions, start with writing down everything you know. Here we know the mass is 33 kilograms. We also know the coefficient of static friction is 0.56. We also know we are wanting to move this box, so our applied force is equal to our maximum static friction because it is currently not moving. Next, as with all force questions, we will draw a free body diagram. Here in this question, we have gravity pulling the object down, normal force pushing the object up, the applied force pushing the object forward, and the friction force pulling the object back. As this object is just started to move, we can assume at this point everything is balanced and our net force is totally equal to 0. Therefore, we know that the normal force is equal to the gravitational force, and as we have stated above, our applied force is equal to our force of friction. Next, we want to relate these together, and we see we have our friction force on one side is equal to the coefficient of friction multiplied by the normal force. Here, our friction force is our applied force, and our normal force is our force of gravity. The applied force that we need is equal to the coefficient times the mass times the gravity, which is equal to 0.56 times 33 times 9.8. Doing the calculation of these numbers, we find the applied force we need is 181.104 newtons. With the correct significant figures, we have 1.8 times 10 to the 2 newtons. This is a question we have seen 2 lessons ago. What if this box was in an elevator and the elevator accelerated up at 2 meters per second squared? How would that change the question? Well, similar to above, we are going to start with what we know. We know our mass is still 33 kilograms. We know the coefficient is equal to 0.56. We also know we are just starting to move, so our applied force is equal to our force of friction. Here, however, we have an acceleration of 2.0 meters per second squared up. This will change our free body diagram. In our free body diagram, we still have our force of gravity, our normal force, our applied force, and our force of friction. The difference now is we have an acceleration upwards of 2.0 meters per second up. Therefore, the net force is no longer 0, and we cannot jump to the equalities we've had before. The difference in this question now comes from our apparent weight. The normal force is no longer equal to the force of gravity because F net is no longer 0. To find our normal force, we must look at the net force. It is equal to the normal force pulling up minus the force of gravity pulling down. Therefore, our normal force is now equal to our F net plus Fg. The rest of the work, however, is the same. We start with our friction force being equal to mu Fn. Our friction force is still the applied force. Mu is still the coefficient of static friction. However, Fn is now the net force plus the gravitational force. Now, for this question, our applied force is equal to the coefficient of static friction multiplied by F net is equal to our mass times acceleration. Fg is m times g. This step is unnecessary, but it makes the question easier. You notice that there are m's in both of the terms here, so you can pull out one mass from the equation and left with a plus g. So in the end, our applied force is equal to our coefficient of static friction times our mass times 2 plus 9.8, and now our applied force is equal to 218.064 newtons. With the proper amount of sig figs, we have 2.2 times 10 to the 2 newtons. This number is bigger than what we had before. This matches what we know of friction. As our normal force increased, we have pushed the objects together harder, and our force of friction has increased. Similarly, what would happen if the box in the elevator is accelerating down at 1.3 meters per second squared? This is a similar question as before, and here we will again start with writing down what we know. We know our mass is still 33 kilograms. Our coefficient is still 0.56, and the applied force is still equal to the force of static friction. The difference now is acceleration is 1.3 meters per second squared down. This only makes a small change in our free body diagram. In our free body diagram, we still have gravity pulling us down, normal force pulling us up, our applied force pushing us forward, and the force of friction holding the box back. Here, the difference is acceleration is now down at 1.3. Since acceleration is down, we know that the F net is also moving down, and because it is down, we will put our F net as negative. Our F net is equal to our normal force pulling up, positive, minus our gravitational force pulling down, negative. Dealing with the signs of the forces in this step essentially takes out the requirements of the vector. As before, we are trying to find our Fn, and our Fn is equal to now Fg minus F net. And as before, our force of friction is equal to mu Fn. Force of friction is equal to the applied force, mu times Fn. Fn is now Fg minus F net. And here our applied force is equal to mu times mg minus ma, and we get Fa equals mu m times g minus a. Plugging in the numbers, we find 0.56 times 3.3 multiplied by 9.8 minus 1.3. Putting these numbers together, we find our force is 157.08, or with proper sig figs, we have 1.6 times 10 to the 2 newtons. Here, the calculations match with what we know should happen. The downward acceleration has lowered the normal force, and a lower normal force has created a lower friction. Now that we have dealt with the friction of objects being accelerated, let us try to change the normal force in a different way. Another way to change the normal force is for an outside force to act on the object as well. In the next problems, we will start pulling on an angle. For example, what is the normal force of a 22 kilogram object if you pull up on it with 50 newtons forward 22 degrees up? Again, like any other question, we will start by writing down what we know. We know the mass of this object is 22 kilograms. We also know we have an applied force of 50 newtons, and this is forward 22 degrees up. Here, just like with any other force question, we will draw a free body diagram. In our free body diagram, we have our gravity pulling us down, we have our normal force pulling us up, and we also have an applied force pulling up at an angle. This angle is forward 22 degrees up. Much like how you may have seen with projectiles in the past, a two-dimensional question is difficult in physics, so we will break this two-dimensional force into its component pieces. The applied force of 50 newtons can be broken down into its x component and its y component. The x component can be found by using the sine of the angle, and this is equal to x over 50. The x component of this is now 50 times sine 22. Similarly, the y component is equal to 50 times cosine of 22. So now, instead of having a difficult question with 3 forces, you have a simpler question with 4 forces. Your 4 forces are the force of gravity, the normal force. These are still here. We did nothing with them. You now have the y component of your applied force and an x component of your applied force. Here, assuming the object is not moving up or down, we can state that the net force is equal to 0 in the y direction. In that case, if our F net is equal to 0, we have our normal force pulling up, we have our force of gravity pulling down like we have before. However, now we have the y component of our applied force helping the normal force pull it up. In that case, the normal force, or the apparent weight, is equal to the force of gravity minus the y component of the applied force. Here, the force of gravity is equal to mg, and the y component of the applied force is equal to the applied force times cosine theta. Using this information, we can find that the normal force is equal to 22 times 9.8 minus 50 times cosine 22. So this is equal to 169.2408 newtons, Or with sig figs, this is equal to 1.7 times 10 to the 2 newtons. Because you are pulling slightly up on this box, the normal force, which should have been 200 newtons, is now 169 newtons. You are helping the ground pull the box up and fight gravity, so the normal force does not have to do as much. Now in this situation, if this force is able to move the object, what is the coefficient of static friction? So let's look back. Here we will save this number because we will need the normal force in our friction equation. If this force is able to move this object, that means the x component of our applied force was able to exactly cancel out the static friction. Here we also know the static friction is equal to mu Fn, and the normal force we calculated in the earlier question. In that case, this is a simple matter of having our coefficient equal to the x component of our applied force divided by the normal force. Here, as we saw above, this is equal to the applied force times sine 22, and the normal force is equal to mg minus the applied force times cos 22. Plugging in the numbers we have 50 sine 22 over 22 times 9.8 minus 50 cosine 22, and this is equal to 0.110672. Or with the correct sig figs, this is equal to 0.11. When you do these questions, be careful with this direction. Pay special attention to this direction, as a small change in this will change your answers completely. If this direction had been down, the normal force would be greater than normal because now you are helping gravity fight against the normal force. If the order of these directions have been flipped to say up 22 degrees forward, the angle would have been from up to the line instead of forward to the line, and your triangle would have been different as well. Lastly, let's look at inclined surfaces. What is the normal force of a 20 kilogram box on a 25-degree ramp? The earlier questions were hopefully simple enough that you could imagine the situation in your head. However, sometimes it is easier to draw the picture. In this case, our first step will be to draw the picture. In this situation, we have a ramp at 25 degrees, and on top of this ramp, we have a box that is 20 kilograms. We wish to find the normal force on this box. Remember, the normal force is always perpendicular to the surface. Since the box is at 25 degrees, the normal force will also be slightly off by 25 degrees. Here, our next step is always to write down what we know. We know our mass is 20 kilograms. We also know our angle is 25 degrees. Here, we also know that the object is not flying off of this ramp or moving into the ramp, so we can say that the net force perpendicular to this ramp is equal to 0. Here, you may not know what to do next, but we know as we have forces involved and we have net forces involved, we can draw a free body diagram. We have our force of gravity always pulling straight down. We now have our normal force is pulling at a slight angle from the norm. We now have a two-dimensional question, which can always be broken down into its components. In the past, since the normal force is the one on the angle, we would break that down to find its y and its x pieces. However, in this case, that does not work. We know that the normal force will only fight against any component of gravity that is pushing into its surface. So here, the appropriate force to break down into components would not be the normal force, but in fact, the force of gravity. Here we have the component of the force of gravity perpendicular to the surface, and the component of the force of gravity parallel to the surface. Now we see our next step is to break down gravity into its two components. Here we have our force of gravity, which is pulling straight down. We also have our perpendicular component and our parallel component of the gravity. Here, where the components meet will always be your 90-degree angle because you can only break down the perpendicular components of a force. We now have a triangle with two pieces of information. However, we need a third piece. We need to find one of the angles on this triangle. From the picture, we can see that we have our ramp is at 25 degrees. Gravity is always pulling vertically down, and we have our perpendicular component perpendicular to the ramp. Here, using our knowledge of trigonometry, we can find that this angle is 90 minus 25, and this angle is 90 minus 90 minus 25. Therefore, this angle here must also be 25 degrees. So this angle in this triangle is 25 degrees. Now we must find our perpendicular component because, as shown in our free body diagram, our perpendicular component is the one canceling the normal force. Here, using simple trigonometry you have learned from math, we know that the perpendicular component of gravity is equal to the total gravity multiplied by cosine 25. We know the normal force is equal to the perpendicular component of gravity, which is equal to Fg times cos theta. We know Fg is m times g. We know the mass is 20 kilograms, gravity is 9.8, and our angle is 25 degrees. Putting everything together, we find that the normal force of this box is 177.64 newtons, or to proper sig figs, 1.8 times 10 to the 2 newtons. So this shows having an inclined surface would change the normal force of a 20 kilogram box. You may have noticed that the normal force is only canceling out the perpendicular component of gravity. So what is the rest of gravity doing? In this question, we have broken down gravity into its two component parts, perpendicular to the ramp and parallel with the ramp. The normal force has cancelled out the perpendicular portion of gravity, and we are left only with the parallel portion of gravity. According to Newton's laws, if we have an unbalanced force, this object will start to accelerate down the ramp. This is why in real life you will see objects sliding at an angle down a ramp, even though the only force acting on it is gravity pulling it straight down. That is because the normal force is cancelling out a portion of gravity. According to this picture, every box on an angle should be sliding down because there will be a parallel portion of gravity. But in real life, some boxes don't slide. Why do those boxes not slide down the ramp? Simply, that is because in real life we also have friction pulling the box up. So there are still three forces acting on this box, and the normal force and friction are working together to cancel out gravity. In this case, if this box is not moving, we know that the force of friction is canceling out and equal to the parallel component of gravity. You may see questions like that in the future, but not today. This is everything for advanced friction. Thank you for watching.